home, you're just dead and buried. Right? It's very tiresome. And it's an open book, by the way. So you can take all the books you want, but still nothing would be there. And you really have to be good. So, and being a PhD and writing that, right? So if you flunk, it's a shame also. So there is an additional responsibility, and somehow I survived. And in the meantime, I also, they told me that, you're too technical, you need to know some, a little bit of basics on, business aspects of that. So they said that you should do an MBA. So I also registered for an MBA at the same university, University of Alabama, and got my MBA degree in 2009. And then I took this exam. So almost like from 94 to 2010, for 16 years I was in school continuously. So now, at that time, I am not fearful of exams. At that time, I know any exam you give, I will know to prepare, I will know to write the exam. So that was the state of affairs. So then, I think we're still doing something. That exposure also good, because every time you think more about technical things, you don't understand the business aspects, right? How money is important, sometimes you don't realize that, because the guy who runs the business will understand money. You can keep talking about technical things, but at the end of the day, the bottom line is, doesn't matter whether you are saving money in materials or manpower, finally are you saving or not, right? So that becomes very important. I learned a good bit of that, and I grew up in a family who does a lot of financing. So naturally my choice was actually to take up finance, and it was a very interesting exercise. I learned many things about finance, advanced finance, basic finance. There's a course called International Finance, Treasury Management, Portfolio, Risk Assessment. Now at least I can have an intelligent conversation with somebody outside my expertise in structural engineering. I can talk a little bit. So that was actually a good value addition that I got. And at that time, interestingly, after I completed my PE, there was a rule in the US that if you have to teach a design course, a person with a PhD should not teach, a person with a license, PE license, should only teach a design course. A theory course can be taught by anybody, any faculty member. So they were trying to recruit faculty members who already have a PE license, so they can do research as well as teach design courses, because hiring somebody just for teaching design courses would be not the, it might cost more. So that's what they were thinking. And I used to be nice with everybody, even now today. Okay, so one of the faculty members who was adjacent to my office was actually Singaporean Chinese. Since I did my master's in Singapore, his name was Shannon Chen. He goes by Dr. Chin, now Professor Chin. So I nicely talked with him. He was just, a new young faculty. And we had a good chat, and he knows me that I work very late, and I also work good quality work. And for some reason, he moved from University of Alabama, and he went to University of North Carolina, Charlotte. And I stayed there. I completed my PhD. I went for a job and got my P license. Then one fine day, he called me and said that there is a job there, right, in University of Alabama, North Carolina. You just apply. I've already spoken. We need somebody with steel expertise. Don't worry. Okay, he told me sometime, and within 24 hours, he again called me and said that I have spoken to everybody. The chair of the committee is also an Indian, has already spoken. I know him very well. And the department chair is now coming from Houston to Charlotte via Birmingham. Okay, do one thing, you don't have to come there. You just, I'll give you his phone number, you talk to him, go to Starbucks, have a cup of coffee with him, chat with him, that is considered as interview, and you come and join. So that was interesting, because the amount of rigorousness that we do in selecting a faculty member, and that was very interesting. Because once they have made up their mind, they know who they are, they'll go out of their way to hire. And that is when I spoke to my folks, and they said that no, you are overstayed your period. You went to study and then you also got a job, you have been there. better pack and come back. So then I had no choice, so I had to come back. But I always had a feeling to come back, but when my parents, especially my mother, told me to come back, so I decided to come back. And I came to IIT Hyderabad. This was in 2012. And there also nobody was in steel structures, so they're really looking for, because every faculty member application they get was in concrete structures, so they needed somebody in steel. So I started my career here at, academic career here at IIT. So this is our building that we are sitting at the back here. And to start with my research activities, I'll give you a brief introduction about my research activities. This is kind of an old slide, but we call ourselves as the Structural Steel Research Group. Right? I stole this name from my master's advisor who used to have Structural Steel Research Group at NUS. So I inspired, since it's no more, I just took that name and started Structural Steel Research Group here. And we work on a variety of things. So we work on wall panels. We began working on wall panels. Today's talk is mostly about wall panels. And in wall panels, we talked about studs and sheathing. And the talk that I'm going to give today on wall panels is basically on out-of-plane bending. But we are also working on in-plane shear right now as we speak. And we also studied imperfections. We were perhaps the first in the world to use a 3D laser scanner to measure imperfections for cold-formed steel structures. 3D scanner was available, but usually used by aerospace engineers to understand the blades, what is the imperfection in the blades and things like that. You see the engine. The engine is the most important thing. So if you have any imperfection in the engine, that could lead to collapse, especially for aircrafts. But we used it for cold-formed steel, and we came up with a good number of results, and we published in Journal of Structural Engineering. We also work on floor panels. Basically, we call it sustainable lightweight floor slabs, because in any steel structure, you can recycle, say, beams, you can recycle columns, but the only thing that you cannot recycle is the flooring system, because floor usually is made of concrete. So it's cast in situ, so you have to break and demolish. So is there a possibility that we can recycle the flooring system, right? Can we come up with a panelized flooring system? At the end of the design life, can we remove the nuts and the bolts and take it to someplace else and start doing things? So we worked on it, and we got a good work on this one, and we are continuing to work on this area. We had a PhD student who completed in this area. At work, during my work in the US, I understood the importance of connections, because the most important thing in any structure is the connections, right? So mostly people make mistakes in connections because connections are catastrophic. So you need to really understand the connections. I was very lucky to work with very senior people. So I had 3 bosses. Each were almost, one was 62, one was 65, one was 64. So each had 30 plus years of experience, right? One was from Taiwan, another was an American, and both really grilled me, right? So whenever you do something with the computer, they would not trust you. They would ask you for a detailed manual calculation to do everything piece by piece, and then they check you, only then they will allow you to do anything. So it was a good exercise, and connections usually require hand calculations. And I also worked with someone who started the first connection company in the US. Basically, there is one person called Bo Dowswell. He was my colleague while I was doing my PhD. He was very senior to me in age, but we actually were sitting together in the classes, and then we also were colleagues at work. And he was an expert in connections, so we used to discuss a lot. So I naturally got excited about connections. And today we do a lot of studies on connections. So we study on member-to-member, purlins. Now we have extended, this is an older slide, but we have extended to beams, beams to columns. We also study welded connections, clip angles, 2-bolted, 3-bolted, flange strip, moment connections. And we are perhaps the first in the world to have classified the connections for cold-formed steel. So connections in hot rolled steel have been classified. If you go to IS 800, the last page of the appendix gives you the details about how radar how they came up with the rigid, semi-rigid and flexible connections, right? But so similar to that, we have also studied the connection classifications for beam to columns, and our studies indicate that it's very difficult to achieve rigid connections in cold formed steel. At the max, you can achieve what is known as semi-rigid, right? And then we also work on built-up sections. Basically, I'm interested in mid-rise construction. When it comes to mid-rise constructions, it is 8 to 10 stories, and you need a bigger cross section to take it to 8 to 10 stories. And what will happen is that when you have a bigger cross section, C channels by default have the shear center and the centroid do not coincide, right? You know what is the shear center? You know what is the shear center? So if you don't know, shear center is a magical point in the cross section. When you apply the load through the shear center, right, it will only bend, not twist. That's the biggest contribution of shear center, right? It doesn't matter which way you apply the load. You apply the load top to bottom, bottom to top, left to right, right to left, doesn't matter. As long as the load passes through the shear center, you are guaranteed of one thing, which is it will bend, not twist, right? But it can bend in minor axis, it can bend in major axis, but it will bend, right? So C channels have shear center and the centroid, there is a big gap. When you have a big gap between shear center and the centroid, the problem is it will tend to twist. When you tend to twist, it will create what is known as torsional buckling, lateral torsional buckling, or flexural torsional buckling. These are things that you wanted to avoid, right? Why do you think that most people construct straight houses like this, everything is square, rectangle in civil engineering? Because they avoid torsion. If you have eccentricity, you will have torsion. So in order to avoid torsion, you always use for a very, very regular cross sections. So what we did was that we understood that it is very, very important to have to neutralize this. One way to neutralize this is to convert a singly symmetric section to a doubly symmetric section by putting two C channels back to back. So when you put two C channels back to back, then it becomes more like an I section, and then the shear center and the centroid naturally coincides. That is number one. So you avoid torsional buckling, lateral torsional buckling, or flexural torsional buckling. Number two, it is also increasing your load carrying capacity, because more bigger the cross section, you can take it for mid-rise constructions. Now the question is, how safe is your structure? How vulnerable? At ultimate load, do you think the cross sections will behave in the same manner? Yes or no? We don't know. So we studied with screws. Then we don't know what at ultimate level the screws will come up, because we did not put enough screws. So should we put more screws? What is the diameter of the screw? What is the length of the screw? What is the spacing between the screw? All these things are questions that needs to be answered. So we are looking at it. We are also working on welding. When we do welding, all right, what is the thickness of the weld? What should be the deposition of the weld? That depends upon the heat input. Heat input is a function of your voltage and also the wire feed, as well as the rate at which the carriage is moving. So all these factors determine the thickness. What should be the minimum thickness? Our studies indicate it should have to be 20% more than the parent metal thickness. So if you have a 1 mm thick steel, you should have 1.2 mm thick as the welding thickness, right? Now how do we determine whether it has reached 1.2? So we have to cut it, we have to polish it, put it under an optical microscope to understand what is the thickness that it has achieved, right? Now, due to welding, there is some kind of a residual stresses that has also been built in, right? The residual stresses are something that will happen. What do you happen? There is a thermal stresses that are happening. Due to thermal stresses, will there be any reduction in capacity? That is something that we are studying. So just to give you a glimpse of that. And many people perhaps may not know, there are two families, right? We have been talking about cold formed steel, but we also come from a parent family called hot rolled steel, right? So this is cold formed steel, as you can see here, but this is hot rolled steel. What do you think is the major difference between cold formed and hot steel? Just looking at it. Looking at the two pictures, what is the difference between hot roll and cold form?
Complex cross.
Yes, it has not only complex, it has weird cross sections. Let it put it that way. It has a weird cross section, right? And it has a very standardized cross section. Say these are all I sections, right? It has a very standardized cross section. That is why you have IS 808, which tells you what is the length of the member, what is the width of the member, thickness of the flange, thickness of the web, root radius, toe radius, everything is given in IS 808, right? But when it comes to cold formed steel, you have no such things, right? Because cold formed steel, you are the captain of your own ship. You determine whatever cross section you think is you like. As long as it is satisfying the stress and strain criteria, that is fine, right? So cold formed steel by default is something that it lends itself to optimization, and creativity, so you can come up with your own cross sections. Right? That is number one. Number two is that hot rolled steels are very expensive. Hot rolled steels are made from a huge factory. They are factory made products, and it's a 10,000 crore industry. The investment, minimum investment to have a integrated steel manufacturing unit is 10,000 crores. Not many people can do that. You really have to have a lot of backing, finance to start a power, steel industry. So either government has to do that, or very, 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 very high net worth individuals can do that. So it is something that is very, very difficult, right? But it employs lots of people, chemistry people, chemical engineering, metallurgists, all kinds of people are required to run a industry like this, right? But cold form steel is basically more like a cottage industry. You can purchase the cold form coils from JSW or Tata Steel, and you can have a press brake machine in your, backyard, and you can press brake the machines and you can produce your own cross sections and sell it. So that is something that you need not worry about other things, and it can be fabricated at the site also, right? And more importantly is that hot rolled steel sections are designed, the cross sections are dimensioned such that it will not undergo local buckling. So you look at hot rolled steel basically, even the B/T ratios are determined, the width to thickness ratios are determined such that, or fabricated such that it will not undergo local buckling. But in cold form steel, it will undergo global buckling and local buckling. So that is something that you need to understand. So what is cold form steel? Cold form steel are members that are made into any required shape by bending or rolling a flat sheet at a room temperature. Whereas if you see the cold form steel on the right side, right, it's lightweight, it is easy to construct, it is cost effective, but more often it is over designed. Why do you over design a cold form steel? Because we don't have proper design specifications, right? We don't have, today the IS 801 is under revision for the last 2 to 3 years. We started working on IS 801 for almost several years back, 4 years back. Right? We have completed at least 2 years back, and it is still under revision and things like that, right? But prior to that, when was cold form steel code written? 1975. So for 50 years, we have not changed the code. That itself indicates that we have not paid attention in terms of funding adequate research, or have not understood the importance of cold form steel. So that means that we don't have proper design specifications. If you don't have proper design specification, what do?
Testing results.
Testing, how many tests, madam, you can do? It's very difficult testing, right? You do some calculations, right? And what do? You multiply by 2 and make the member. See, as an engineer, you don't have a choice to say no. You work for an organization, I'll tell you that I've worked in enough. You cannot say no to your boss. Otherwise, somebody will fill your this thing. You have to deliver, right? So rather than optimizing it, what do? You have some idea, but you're also a little worried. So you multiply by 2 all the stresses and then design a cross section and give it. Aram say it will work, right? But rather than saying no, you get it done, right? So one of my teachers in the US told me that if you know what you're doing, it is called factor of safety. If you don't know what you're doing, it is called factor of ignorance, right? Either you do it right and have a factor of safety, or if you don't know anything, multiply by 2 or 3 and then get it done. Okay, I think this is something that we are going to cover, but I'll just give you a brief overview of this one, and this is what we are going to cover in this topic. So this is a typical wall frame. You see that there is a top track, bottom track, and then you have studs here, and then you have a lot of bracings, chevron type bracings here, right? What we wanted to do is that, is it possible, can we remove all the bracings and we can have 3 studs and put a sheathing, exterior sheathing, which we are going to do anyways, right? We put plywood, we put gypsum board, and we put screws and connect it. Can we not take advantage of the sheathing and remove this, this excessive amount of bracings that you put inside? That will result in savings in steel. So that is our goal, right, which will come. And we also studied geometric imperfections, CFS geometric imperfection. Why imperfections are important? What is an imperfection? Anybody know what is an imperfection? What is an imperfection?
which an imperfectionist member, and given as a geometric imperfection due to which the initial movement will be generated before applying the load.
Right. So there is imperfection is deviation from ideal cross section is an imperfection. Deviation from an ideal cross section is an imperfection. Right? I always used to say that there is nothing imperfect. Nobody is imperfect. Nobody is Ram or Ravan. Everybody is in between, if you look at it. Right? Likewise, in steel structures also, you don't have perfect structures. You always have imperfect structures. But how imperfect can you tolerate? That is more important. So we have to measure, we have to quantify the imperfections in order to make sure that whether we are able to use the imperfections or not. Right? So that quantification so far was not done properly in our opinion. So we ventured into this imperfection using a 3D scanner, and we came up with a lot of different results. One thing that we were really worried is this AISI, which says that, you know, these imperfections are all the same regardless of the depth, the thickness, the imperfections are the same. It is measured only in length. If you have 1 meter, the imperfection is 1 mm. If you have 3 meters, the imperfection is 3 mm. It doesn't matter the channel is 5 mm, you know, 50 mm deep or 500 mm deep. They say that the imperfection is irrespective of the cross section. It can be a C channel, it can be a hat section, it can be a Z section. In our opinion, that is fundamentally flawed. Okay, so they basically use one size fits all, and these are the different variations and imperfections that are available. There are two categories. One is called a global imperfection, another is called a local imperfection. The global imperfection gives you what is known as bow, camber and twist. Bow is minor axis imperfection, camber is major axis imperfection, and twist is the imperfection in the along the length where it is twisting, right? So these are the three major global imperfections that are there. The other imperfections are crown, okay, dent, flare and overbend. These are all called local imperfections. So you have 6 different types of imperfection, 3 global, 3 local, and all of which has to be measured carefully in order to classify, categorize the cross section for use in cold form steel members. And we did close to 188 specimens. This is one of the largest tested specimens that we have. For the same specimen, we would have done 6 times. So you say C1 is the specimen number. The next 6 is we manufactured 6 specimens same time, and then we measured it 6 different times. Because imperfection is also based on the quality of the manpower that we have, right? Why do we need imperfections? Can somebody else do that? Why Indians should do that? Because Indian manufacturers will produce different types of imperfections, and American manufacturers will produce different types of imperfections if he is using a press brake. So we cannot say that that results from US is valid or Australia is valid. You cannot say that. So for our own code, we have to develop our own imperfection standards. So that's why we carried out 188 different types. We 3D scanned. So for each specimen, we got all close to 81,000 data points. So for every mm along the length, we measured it. So the specimen is 3 meters. Why 3 meters? Because each floor is tends to 10 feet. So we measured it for 3 meters is 10 feet. So for each column, we decided to carry out 81,000 data points, because we have 27 data points per cross section, and then into 3,000 gives you that. So this gives you a fundamental understanding of how the imperfections are. Now, as I told, the definition of imperfection is deviations from ideal geometry. So what did we do? We superimpose the actual profile with the ideal 3D AutoCAD geometry, and we understood what was the imperfection in the cross section along the length, and we started measuring that, and we classified, categorized that in 6 different forms. So these are some of the classification imperfections. This is a very famous paper. We have got more than 100 citations for this paper here. It went for almost 5 reviews. Each review was like a thesis. They ask you 100 questions and you have to answer 100 questions, and then it goes, and after a month you get another 100 questions, you answer another 100 questions. The fundamental reason is why a dark-skinned Indian is worrying about American codes. Right? So we were working here because we had no other choice. We were using basically an Indian, American code, because we did not have a code, but we also find a lot of flaws in American code. So we started looking at it, and that's what we got lots of things here, right? So this basically gives you how we classified, categorized the imperfections. More details can be obtained here, right? As I told you, every publications that we have, it's already updated in the website. We get published within a day or two, we are updated, right? So it's all available. You can go click the publication link, download it, read it, enhance yourself, right? We tell you, I always tell, don't trust anybody. Rule number one in life, never trust anybody, right? Always read by yourself, understand, make sure that the knowledge is yours, right? He said so, they said so, no. Go to the original source, understand it, right? With scientific data. Now, this is the equations that we came up with. We classified the imperfections with regard to the slenderness. So if it is for a bow, it is L by Ry, which is the slenderness for minor axis. With camber, it is L by Rx, slenderness for major axis. And twist, we came up with a new parameter J by L to fit the curve. And then for flare, crown, we had similar imperfections. So this is for imperfections. We also work on strengthening of steel structures. Basically, we are also looking at how to use the existing steel structures. If they are corroded, can we do something about it? So this is strengthening of steel structures. Basically, we attach a cold form steel to the hot rolled steel, transform the cross section from an open section to a closed section, thereby increasing the torsional resistance. So this is a very simple technique that we can do rather than doing anything. So this is shift in shear center due to closer to centroid. So this is, okay, for this one you see that shear center is here, centroid is here, right? So when I put something like this, the shear center is moving closer to the centroid, which means that you are reducing the amount of bulky that it is doing. It does not twist or turn. As and when you come closer to the centroid, the shear center is moving towards the centroid, will have less. Right? So this is what we did, and then it actually resulted in a very good load carrying capacity. We have published lots of papers on this one as well. And we also use not only cold form steel, the one that you see is cold form steel. This is retrofitting of steel structures. We also used CFRP for strengthening cold form steel, right? CFRP has been successfully used for concrete, but why not for steel? There's a lot of resistance here within my, campus as well as outside. Who are you? Why are you doing this? CFRP is used only for concrete. It will never work for steel. Blah 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 blah. So you tell what you want to do. I'll do what I wanted to do. Right? Research is something interesting. So we did, and actually we got very good results, and we have been able to successfully demonstrate the applicability of using CFRP. And this is unidirectional CFRP. This is bidirectional CFRP. We studied for angle sections, angles with plates. And this is something that we can be applied here in order to prevent lateral bending and twisting. Right? Connections, as I told, very interesting. We study on beam-to-beam connections. We study on beam-to-column connections. We also have purlin-to-purlin connections. So many different types of connections that we study. And there's a lot of papers that are available in the web on connections. Right? Most of the connection details that we talk about is not even available in any of the codes. Right? So we have design equations, tested results. We also have design examples, how to use that. So if you really wanted to apply any connection in your industry, you can take it, download it, read it, understand it, apply it. So we have given the test data, we have formulated the equations, we have also told how to use the equations. Everything is available for free. Most important things in life are free. Right? It's all available, you can download it, right? And these are some of the test results for several things. As you can see, it's complicated. It's not that simple, it's complicated. Connections by default are complicated, but it's always interesting to do complicated things, right? So whatever you see here are the publications corresponding to the pictures here, right? So you can download it and understand it. This is for the clip angle. Again, we came up with several different failure modes for all these clip angles. And the previous one was beam to beam. This is beam to column. We have tested it here. One PhD student, Nathan, he did a lot of work on this one. This is paper at the top, and there is another paper at the bottom. We also wanted to study floor panels. Another PhD student worked on floor panels. So what we did was that we had a cold form steel deck, and then on top of it we put the hot rolled steel plate and then fill between the two with some lightweight mortar so that it can be recycled. We did not want it to be too heavy because it becomes more expensive. Can you tell me what is the most expensive thing in a construction site? Huh? Demolition cost? No, when you're constructing it, not demolition. Most? Huh? Huh?
Shuttering. Scaffoldings.
Huh? You give low money, high money, but there's a separate group called construction management, right? MTech in construction management. Why did you think that started?
For a time.
It's usually the crane. The most expensive equipment in a construction site is the crane. If you look at your construction manager, 90% of the time, he will be optimizing the usage of crane. Right? Every hour is important. The crane cannot be idle. Rule number one, you have to continuously use the crane. Right? When do you need crane? When you pick up very heavy equipment. But if we do things that you don't need heavy equipment to lift using a crane, then life is simpler, cost comes very down, right? And you can make things faster. So what do we do to reduce the weight? We put lightweight mortar. So that was the intention here, so that some two people can lift it and put it in panels, right? So that's what we did here also well.
Is that NCT similar to the LVDT we use for displacement?
Yes, NCT is called non-contact displacement transducer, very similar to LVDT. LVDT actually is good for concrete because concrete will deflect for 2 mm, 4 mm like that. Steel will deflect for 10 mm, 20 mm, 40 mm also, right? So when you deflect too much, if you're using not careful enough, the LVDT could be broken. And each LVDT cost 1 lakh, 1.5 lakhs. Not only the money, LVDT is not manufactured in India, it's usually in the Germany. So the amount of paperwork that you do to get an LVDT is nightmare, right? Plus, as an academician, I want a clean shot, right? When I take a picture of my experimental test setup, I don't want any sidekicks. I just want the picture, specimen, loading frame, how it deflects. That's my intention. So all the garbages I wanted to remove and then look at it. And LVDT was actually a hindrance. Many times it's dominating the picture, right? I don't like it. I want it simple, sweet, nice. So NCDT, that's the trick. You can keep it at the bottom, it has a laser beam and it measures and it gives perfect. Up to two decimal places it gives me. What more do I want, right? So that's why we use NCDTs, right? Good question. And we also wanted to see what is the shear capacity here when we use such things. So we developed a new test frame fixture here and applied it back to back, and we studied what is the capacity of the shear of the screws that are connecting the top hot rolled and the bottom cold form steel. We connected it with the bolts, right? We wanted to understand that. So this is something that we did to understand the number of bolts that are required to prevent slip, because slip is one of the most important things. Once it slips, it doesn't work, right? So we wanted to prevent slip. So how many bolts to put, what diameter of the bolts to put, that has to be determined by this kind of a test setup. This is called pull-out test, right? So you see that it is very carefully designed because we had some hot rolled steel on top cover, because if you put the load directly here, it will locally buckle here. So we have to put a cap here and we have to load it here, and then we push it, and then the load directly goes to the bolts, and we understand the capacity of the bolts, right? So it was an interesting thing that we did, and this is the testing that we did for large scale. We initially did it with small scale, and then we did it for large scale. We also did cyclic test because we wanted to know for a 30-year lifespan, will there be any problem? So we did 5,000 cycles of cyclic test to see that after 5,000 cycles, which simulates 30 years of design life, service life, is there any problem? So after 5,000 cycles, when we looked at it, there is no problem. So which means that it can be validated for a 30-year lifespan. So the beauty about all these things is that after 30 years, you don't want it, you can remove the nuts and the bolts, the flooring, keep it at a place, and then build a new structure, bring it in, and then put it back and put it. It will work.
Did you do any vibration analysis for this?
Yes, we have done the vibration analysis also, and our results indicate that they are very good. In fact, there are pictures that I jumped on it, and my students studied it, and we got a lot of equipments for vibration, and we studied it. It was good.
In terms of the frequency, so there is a notional tendency, like when we walk and if there is a vibration, so it creates a dissonance.
Yes.
There are codal parameters. In terms
So we looked at the codal parameters. We are ensured that sometimes we may have to increase the weight of the concrete to increase the mass. Right? Sometimes you have to increase, because if it is too light, then people don't feel good. Right? Perceptions are very, very important in life. Right? So when you walk, you need to feel really good. If you are dancing in the walking, and it's problem. So we have done all that stuff, and we have been very successful in this one. Right? And right now, the most important person is Godrej is interested in this, because for storage system. Because Godrej has storage racks, and they wanted to put this on top of it, and they wanted to understand how much it is, right? So they are interested in that. So we tested it, we did single bolt, double bolt, and things like that. And the most important thing is the built-up members. We studied built-up members back to back. You can see the test results, the number of screws, and this is the local buckling, this is the flexural buckling here, as you can see, right? And this is how we did it. And you are the first one to put the screws in the opposite direction. Most people, you look at it, they put the screw in this direction, the screw in this direction. We suggested that it should not be done that way, because you never know if both of them or something like that, it could come out. So you need one in this direction, one in the opposite direction, to make sure that they are robust. And this recommendation has been given in IS 801. Hopefully when it comes, this will be there, right? And we also did for built-up beams as well. We did some built-up beams also. We did a lot of testing on these built-up beams. Distortional buckling takes place and things like that. So as of now, there are no design provisions for built-up beams. And we have actually come up with some preliminary design. A lot more work is going on. Currently, one PhD student is working on built-up beams. And we also work on built-up columns. We have now migrated from NCDT to 3D DIC. So we look at 3D DIC, multi-directional 3D DIC setup to understand the buckling. So typically when people do experiments, what do? They take a picture when it is locally buckling and say that specimen failed in local buckling. And when they take a picture when the specimen is in global buckling, they say that it has failed in global buckling. But in reality, our understanding is that it is not same. There is a birth of the specimen, there is a death of the specimen. A specimen goes through a lot of morphing. It changes its character, right? 20 years back, if you ask me, is this good or is this bad? I would say, yeah, this is good, this is bad. Today, if you ask me, I'll say, maybe this is good for these things and this is good for these things. May not be correct, may be correct for certain things. If you apply these things, it is correct. So we kind of classify it, right? So you don't give a straightforward answer, because there is nothing absolutely correct. It's always some thing is there. X is saying something, Y is saying something. There is truth in X, there is truth in Y. You have to figure it out, when is X correct, when is Y correct, right? So similarly, this also, when we do 3D DIC, you can completely understand from the start to the end what is happening with the specimen. The specimen first goes through slightly axial compression, then it fails in local buckling. Local buckling is triggering global buckling, and global buckling is triggering inelastic buckling, right? First it goes through flexural buckling, and then it also starts to twist because there is an eccentricity. So the entire thing is something that I cannot say that this failure is dominated by one particular thing. It takes a huge one from start to end. And how do I capture that? Only by 3D DIC. Right? So I can tell at load 20% of the ultimate it is locally buckling. 30% of the ultimate it may not be local buckling. It is morphed from local buckling to say global buckling. At this stage it is yielding, then it is failing. You have to tell the truth in its entirety. Right? Otherwise when you look at people, when they want to slam at you, they'll just pick one statement out of your this thing, and this guy is telling this one, yes, and 1,000 WhatsApp messages gone. Right? So we have to be very careful. That's why we do the truth as it is in the entirety by capturing the failure of the specimen. Right? This is local buckling. Right? So this is local buckling. You can see that it's very nice. We have lots of cameras. You may ask why we are doing the testing in the night. Right? Because when you do it in the daytime, there's a lot of shadow that comes from the sun. So the results are not very good. So when you do it in the night time, it's the closed environment, we are able to actually understand the behavior in its entirety. Right? So this is using cold form steel built up sections, multi-DIC. So we have one DIC in 0, one in 90, one in 180, one in 270. So we have surrounded it. So we have captured the beast in its entirety, and we can say that what is happening with the specimen in all directions. So using this, we can develop interactive equations, right? So we also do the CMT welding, which we will see that there is a welding machine. We are the first one perhaps to use the CMT welding for cold form steel. CMT welding is called cold metal transfer welding, which we have done using for cold form steel. Cold form steel, typically, you know, if you're not careful enough, you can poke through that. Have you all played with agarbatti and paper in your young age? Don't you make art? You know agarbatti? Right? So you take agarbatti and paper and you can draw Indian, territory, and then like that you can do that. So that is how, if you use the hot rolled steel, you know, this welding rod with cold form steel, it will poke through. Right? Why? Because it is producing excessive heat. So you have to be careful. Cold form steel is like a baby. You have to treat it with care and respect that it deserves. Right? So what do? You have to put some heat, and then you have to keep watching it, and then put some heat and remove it, put some heat. So the loading should not be a point load, it has to be a uniformly distributed load. That CMT welding does that uniformly distributed load because it has welding very carefully done here. So it goes through that, there is a weld spatter, it comes out and then it moves and goes there. When the heat is more, it comes down. So it quickly does it. And this is an Austrian technology by a company called Fronius. So it's an imported machine that will do the welding like a very small, nice stitching, right? So that's what we did, and then we fabricated a lot of specimens. We wanted to understand the behavior of that. So we studied this one. This is the weld that deposited, because at this location, you see that, at this location there is a curve. Hot rolled steel will not have that. Hot rolled steel will have a flat plate. Cold form steel, two back-to-back sections, it will have a curve at that. So that curve, we are putting this weld deposition here. And we did a lot of studies by varying the length of the weld and thickness of the weld. And we wanted to know how much deposition has taken place. Now, to a naked eye, you cannot do that. You can never understand the amount of deposition that has taken place. So what did we do? We actually put it under an optical microscope, right? So we see that if the voltage is 130 amperes and the carriage speed is 330 millimeters per minute, the amount of thickness deposited is 2.279 mm. Right? So from 130, if I jump to 140, right, the carriage speed remains the same. I have increased my voltage. So more heat. More heat means more weld deposition. So I can see from 2.279 it jumps to 2.563. Right? And then when I decrease from 140 to 120, it comes from 2.279, it goes to 2.017. So the amount of heat input is very, very important in order to have the required thickness. Right? So that is a function of your voltage. So you change the voltage and then decrease the amount of weld such that you get whatever thick. You know, it doesn't mean that you get too much weld is good, because too much weld is also bad. Right? In Tamil there is a saying, Alavurukku minjinal amirthamum nanjagum, which means that if you exceed the limit, even amirth, right, amirth, which is the god's food, is also not good. It will become a poison. So too much thing is also not good. So you have to slowly put the amount. So what is that we have come up with? We have told that if your parent metal thickness is T, don't exceed the Lakshman Rekha of 1.2 T, which is 20% more than the thickness of the base metal plate that you can deposit. So that is our results that have demonstrated it. And to do this is not a joke. You have to cut the specimen, you have to polish the specimen, you have to be nice with the guy who has this polishing machine, and you have to take him to coffee, talk to him nicely, say hello to him, bow before him. You have to do many things, and then he has also a lab. Another person has a lab which has the optical microscope, so you have to do the same thing with the fellow who has optical, and then look at the optical microscope, come up with the thickness. So that is how you measure the thickness here. So it's a very, very close-up view that I've shown here. We also understood that the failure here is a function of whether the plate can tear or weld can fail depending upon it. So we came up with a parameter here, and we said that if it exceeds that parameter, it's going to be a weld failure. If it's below this parameter, it's going to be a plate tearing. So something like that we have come up with, and we have published these papers also. Right? So this is very, very important because our objective is to have every Indian as a house. Right? So we cannot afford to have build like this. Right? We are a nation of 1.4 billion. Going horizontal is not going to be feasible. We have to go this way. Now, if I have to go this way, I have to go for a taller structure. If I have to go for a taller structure, I need to use most likely a sustainable material, which is a steel. But hot rolled steel is expensive. Now cost, Indians are price sensitive. So can we not go for a cold form steel? But when you go for a cold form steel, single channels are not going to be helpful. You have to put a doubly symmetric. So in order to doubly symmetric, you have to weld it. In order to weld it, I need to know what is the weld thickness and characteristics, whether it is going to be useful or not. So it directly benefits our construction practices, which will actually help for designing more mid-rise construction. So we also did with built-up beams here. And this is the closer view of how it is, and these are all the specimens that we fabricate for cold metal transfer. So these weld beads are used for metallographic studies. To be honest with you, this is how it is. So we don't want to weld it completely. So we want to weld it and then give a gap, weld it, gap. Because if you do too much welding, right, it kind of distorts. So what is the point when it is already imperfect? The name of connecting two specimens, you cannot destroy the specimen. So we need to know how much weld to put. So this also is a study that we did. And this is the test setup that you can see on the right side. Okay. And we measured the imperfections for this built-up section. After welding, it will test, right? Now you use the 3D scanner to look at it. And this is the experimental test setup for this one, right? One thing is that, you see that this is white in color and this is not white in color. This white in color is basically a number of dots that we put, because 3D DAC requires you to have several dots so that it can measure the base picture, and then once it moves, the dots also moves. So based on the movement of the dots, it will calibrate and it will tell you what is the stress and the strain. So this is the distortional buckling that we observed. Now we also don't keep quiet. We also working with somebody who can do numerical welding of CMT welding. So this is to examine the residual stress effect of CMT welding on CFS channels. What we understand is that when you weld something, there will be thermal stresses. Thermal stresses will lead to residual stresses. Anybody know what is the meaning of residual stress? What is the residual stress?
Stress event during the manufacturing of the steel.
Stress?
Stress which are being incorporated during the manufacturing of member or the cross section due to the temperature mostly. Due to the temperature, the stresses have been generated that are known as residual stiffness. Stresses which are there before application of loading. That is known as residual stress.
So residual stresses, as the name indicates, English is a fantastic language. If you understand it thoroughly, etymology, right? Do you know there is a book called Word Power Made Easy? There's a book, when I was growing up, I read that book. It's a very nice book. Word Power Made Easy by Norman Lewis. Every word can be broken into pieces and you can understand. Right? That concept is called etymology. E-T-Y-M-O-L-O-G-Y, I think so. Right? So residual stresses, as the name indicates, stresses that are residing in the structure before you apply a single kilonewton of load. Stresses that are residing in the structure before a single kilonewton of external load is applied is called residual stress. And those stresses are typically during fabrication, right? So we wanted to quantify that, right? How do we quantify residual stress? That was our interest. So we actually modeled it in Abacus, and we have a moving heat source. What is this moving heat source? The moving heat source is, now we have to start it here and we have to move this heat source and we have to understand what is happening at this location, right? Once it is moving, right, the stresses, the thermal stresses actually is say 1200. When it moves away from that, the 1200 will become 1800. As and when time goes by, it will come to normal temperature. So we wanted to understand what it is doing, how it is locking the stresses. Is there any way we can understand these things, right? So we modeled it in Abacus. People are still working on it. A bigger version of this one is here. So this from here to here, the heat source is moving in order to understand the thermal stresses, right?
Where the damage parameter for this cold form steel by doing this simulation, given by photon.
This one?
Damage parameter. The damage parameter required for this.
Damage parameter, we still in the process of understanding many things. Because what happens is that if you don't know exact heat that you generate, you will not be able to put as an input in Abacus. Now we don't have an equipment to measure the heat, right? When we go ask people, what should I do? They say that what is the temperature range? I say from normal temperature 1200. They say that our cameras can go up to 650, right? What happened to 1200? I say that there is another camera which goes from 500 to 1800. Now I'm getting confused. What to do? Then they say you purchase 2 cameras and each camera is 20 lakhs. Right? So where is it's very, very important. If you have to understand, you have to invest, right? Because you have to really look at it very carefully, where the stresses is starting, where the stresses are ending, how much you should do, all these kinds of things have to be done very carefully. Because if you don't know the input, output is obviously wrong.
Because this is a new material. This is a new material, cold form steel. Where the properties, how the properties were incorporated for this simulation?
Cold form steel is not a new material. Cold form steel may be a new material for Indians, but cold form steel in existence for the last 40 years, 50 years. In fact, if you look at the course that I will teach, for the course, you start with 1910, cold form steel was there. So cold form steel, there is not much difference between, it's just the manufacturing process. The E value of cold form steel is almost the same as the hot rolled steel, except that there is a 5% difference because of the rolling direction, right? Otherwise it is 2 into 10 power 5, right? Yield strength is Fy. So what is the change that you are expecting? What material properties? The failure modes may be different, but the material properties are more or less the same. The failure modes are different simply because the geometry is very thin, right? So things like tearing failure, which may not be present in hot rolled steel, will certainly be in cold form steel, right? Distortional buckling, that is not there in hot rolled steel, will be there in cold form steel, right? Global, local, local, global, local, global, distortional, all these buckling, interaction buckling, right? This will be there in cold form steel. Hot rolled steel, normally it is local buckling and global buckling. There ends the chapter. Look for local buckling, you look for global buckling, you have an interaction equation, end of story. More than likely you have captured the beast. Not with cold form steel. Cold form steel, as you go thinner, it depends upon geometric imperfection, it depends on manufacturing process, depends upon transportation, how do you store it, right? What kind of screws do you put, type of screw, thickness of the screw, is it a regular screw or a power actuated fastener, do you put a bolt, do you weld it, because of welding is there a residual stress? So many questions have to be answered. That's why there is a lot more research have to be conducted in cold form steel. Thinner the material, you invite more problems, right? Yes, there is a fact that the amount of steel consumed is less, right? Yes, that is true. You can accomplish more, but at the same time you have to also take responsibilities in the proper design of cold form steel.
What about the cost aspect?
Cost? I did not look at the cost, right? But when it comes to automation, I think it is the company that has to be designed. But CMT welding, we do only in limited quantities. We are not a production fellow. So that I don't think it's just a welding, that's it, amount of, so it's a special wire, right, and then it's a special machine, that's it. Other than that, the most important things is all same. Only thing is the machine will not do straight, it will go like this, go like this, go like this. So whenever it senses more heat, it will come back and go and come back and go and come back and go. So that is the beauty of this cold metal transfer welding. So in terms of cost, we really don't know. Production, no. But if, say, people understand it and then can automate it, nothing like it.
So can we do still water welding?
What is that?
Still water welding.
Still water welding. You can do any welding you want. Nobody is preventing you from doing it. Now when you weld it, you have to now measure what is the weld thickness, you have to measure what is the residual stresses due to the weld, what is the heat transfer, you have to quantify it. Right? So if I do several different types of welding, you can do all the welding you want. But then quantification for that will have to be done before people can use it. Right? Good. So these are some of the residual stress measurements also here. We can see that. They are measuring the residual stress connections. And then we also wanted to work on apex connection, because cold form steel is typically not used in portal frames. If you look at it, right? If you look at it, this is the apex connection here, right? Portal frames are typically used in hot rolled steel, not in cold form steel. But if you look at it, there's a lot of need for portal frames which are smaller in span. Because if you go to Northeast, lots of people cannot use concrete because concrete is too expensive to be used in Northeast, simply because the raw materials have to be shipped to a very high distance, and it is practically impossible to mix it, fill it up with water, this and all kinds of. If it's a hilly area, you really need something that can be ready-made and used. And Northeast, for example, is one such place where you really need cold form steel. So lots of people have churches there. They don't want big churches, they want small congregation churches which can be done using cold form steel. Lots of Anganwadis, small schools, nursery schools, they require cold form steel. So cold form steel portal frames are actually very, very important. But the problem here is that the apex connection here is very, very unclear. The apex connection in cold form steel is very unclear. And we have come up with some unique configuration here. This is the apex connection here. And this was actually inspired by Professor Kim Rasmussen from University of Sydney. So we were very inspired. There was one student called Rinchen who had done a lot of work on this area. But we found some faults on that also. So we said we'll try to do this, some kind of studies here. And then this is the testing that we did for this apex connection. It's actually a hot rolled rafter and it's a cold form steel connection, and we tested it and we have got some papers published on this one. So we are slowly writing the design rules for that, so eventually it will also become part of the codal provisions. So these are deformed shapes here, and we also from the 3D DAC we can see very clearly how the deformed shapes looks like it. So this is out of plane. 3D DAC is three-dimensional digital image correlation. Most people use 2D DAC because they are using in concrete. Concrete does not have to move this way, just in plane. But steel, it moves in three directions. So if you have to understand it carefully, you have to use 3D DAC to capture this. CFS connections, and we have done some lot of wall panel tests. We'll come back to that because the next topic is going to be that. So we have studied on wall panels. This is out of plane bending, but now we are also looking at full scale test setup for shear. This is the shear loading for wall panels that we are doing here. So we are beginning to understand this also. This is also a large scale test setup that we are trying to do, and to get some understanding of different sheathing configurations, the screw spacing, the connections, the thickness of the sheathing. And we also wanted to understand if the sheathing has to be gypsum, plasterboard, or it can be steel sheathing. How do we do so? All these things are being studied here as we speak. And this is a multi-DAC setup because you have to completely capture, right? So you have to put a 3D DAC here and then a 3D DAC at the back. So to completely capture both the front and the back to understand if there is a failure mode that we don't want to miss it, right? So then we are also studying beam-to-beam connections. At a closer look, this is the new test setup that we have come for beam-to-beam connections. We have also included what is known as a flange strip at the top. We did not have it previously. This is a clip angle, this is a flange strip. The clip angle is used for shear and the flange strip is used for moment. Because anytime when some flange and a flange connection is a moment transfer connection. Web and a web is a shear transfer connection. So when we have clip angles, it is connecting the web of the beam to the web of another beam, so it will only transfer shear. But if you put a flange strip at the top, it is also transferring the moment. So we have studied this. And what we wanted to study is that we also understand that roof is a big problem in cold form steel. Roofing is a very, very, very big problem because in India, seismic is a fancy word. Everybody wants to work in seismic, right? But if you look at it, we have more problems in wind than seismic. Seismic is a probability. Wind is not a probability. A structure may experience earthquake or may not experience earthquake in its lifetime. While it is true that we are experiencing earthquake more often than what we used to experience, wind is cyclic in nature. Look at the amount of infrastructure that we have lost due to wind. Unlike any other nation in the world, we have 7,500 kilometers of coastline covering from Gujarat, come to Kanyakumari, and then from here all the way to Kolkata, right? 7,500 kilometers, 66 wind-prone districts. So we have the three most important valuable cities, Chennai, Mumbai and Kolkata, which are valuable for real estate. Any property in the coastal area is very, very valuable because your trading happens. We get money by shipping things, right? Our foreign exchange increases when we ship things. So coastline is very important. Coastal assets are much more important for a healthy nation, but we have not invested much in terms of understanding the wind, right? If you look at Hudhud, and fail in Odisha, Hudhud in, I think, Andhra, someplace, you will see that wind is creating havoc, but we have not even spent a fraction of money that we spend on earthquake towards spring. And I've been writing proposals after proposals to so many people, but I've done what I should do for wind. So we are actually working on understanding the uplift of purlin to rafter connection. There are two types of connections in roofing, right? You have a rafter, right? You know what I'm talking, it's a rafter. And top of a rafter you have a purlin. And then on top of the purlin you have a sheet, right? So there is a connection between the purlin and the rafter, and there is a connection between the purlin and the roof sheet, right? Most people have studied the connection between the roof sheet and the purlin. Not many people have studied the connection between the purlin and the rafter. So we wanted to study that because failure either happens there or happens at the bottom. Failure is a failure, right? You can lose a beam in your, in your infrastructure. You can fix it. We may even afford to lose a column. Still, you can fix it. If you lose your roof, gone case, right? Roofing is most important. Even if you look at it, any construction, you may not even go to the construction site for your house, but the contractor will tell you when he is pouring the concrete on the roof, he'll call you. Have you noticed it? You talk to any contractor, he will call you and he wants you to witness your house, how the concrete is poured when roofing is done, at least for the first floor or roofing. That's the most important thing. You cannot afford to lose roof in your infrastructure, right? Now, having said that, you have developed one of the largest pressure box vessels. Here this is 7.5 meters and 3.5 meters in length. So we have a pressure loading actuator here. We pump the one here and we apply the pressure to understand how the behavior is happening. So in terms of two things, two roofing sheets, what are the number of screws to be put, what is the length, how to understand the behavior. Because unless you do experiments, you will never be able to tell the truth. Finite elements are good, but finite elements you can tweak it in whatever way. You modify the loading criteria, it will give a different result. You modify the Young's modulus, it will give you a different result. There's a lot of tweaking you can do, but this will tell the truth. Experiments don't lie if you do it properly. They'll always tell the truth. It may be an ugly truth, but it will tell you the truth. right? It is for us to decipher and understand what exactly it is telling, right? So when you do the experiments, you can be really, really nice to get a lot of data. And we have started with connections here, the pull-out connections, but we are also studying this entire thing. And this is perhaps one of the largest pressure box vessels that we have, I think the one in India. So we are also looking at some numerical studies, how the loading is being carried out at this location, but still in preliminary stages. And having said that, at IIT Hyderabad we have developed a laser scanning lab, structural mechanics lab, and several other labs that we will show you in the day or two. Right? This is our labs here. This is a QAQC lab. We have all these things, structural engineering lab, structural mechanics lab. This is the 3D scanner lab that we have. Thank you. So this is brief overview. We'll have a tea break and then come back and start on direct strength stiffness method. And any questions, comments?
I'm going to this. So, how will you incorporate the stiffness of the sheeting member in designing, by designing the stud frame for a ball panel? So, how will you incorporate? Because you can't incorporate that stiffness to the stud and you can't provide bracing for to incorporate that.
Right. So the stiffness has to be determined based on the screws. The screws will tell you what stiffness has to be designed. Each screw can be idealized as Kx, Ky and Kφ, and then the formulas for Kx, Ky, Kφ are given in RP13 of AISI 2013. Right? You can download it. You can get 3 stiffness. Put all the stiffness in CUFSM. It's called Cornell University Finite Step Method. It will give you the stiffness, and then that stiffness has to be incorporated. Incorporated in the CUFSM, and you get a cold form steel with additional stiffness. That will determine your FCRL, FCRD, FCRE. Then you go ahead and plug it in DSSM and you get the results. So you have to use the equations that are given there. But that there also is a lot of flaws are there. So wait for the next session. Right? Thank you. Okay, guys, we'll break for tea. So, welcome back. So, we'll talk about direct strength stiffness method, right? So, I had a PhD student and he was working on a problem. He wanted to work on columns because cold form steel columns are always interesting. Right? It gives you different mode shapes. It's very interesting. Columns actually are very interesting. It will bend, it will buckle, right? By the way, anybody know what is the difference between bending and buckling? What is it? Huh? How is it?
Major axis. Minor axis will be load.
Major axis bending, minor axis buckling.
When load is acting about major axis. When we get here.
Okay.
When load is acting minor axis, it will be buckling.
Say for example, I give you a tested specimen, right? The tested specimen is curved like this, right? I am not going to tell you whether it is bent or buckled, but it is a curved specimen. It has been tested. Can you, from the specimen, can you tell me whether the member was subjected to major axis or minor axis?
Take place along the direction of the load. The buckling will take place perpendicular.
That's the perfect answer. So the difference between bending and buckling is not about the direction of loading. It is the direction of displacement. Right? If I apply a load and the specimen moves in the same direction as the load, it's bending. And I'm applying a load and the specimen is moving 90 degrees perpendicular to the direction of loading, it's called buckling. Right? So from the tested specimen, I cannot understand whether it is bending or buckling. Why? Because the resistance to bending and the resistance to buckling is both EI, is the flexural stiffness. The bending equation is a function of EI. The serviceability is delta equal to 584 by 3 EI, whatever it is, but in the bottom it will be EI. Right? More the EI, less the deflection. So that is correlated to bending. Buckling equation also P critical is pi square EI. Right? So the EI is the hero. The resistance to bending and buckling is offered by EI and only by EI. Right? But the only difference between bending and buckling is the direction of displacement. Right? Okay. So we wanted to study buckling, but unfortunately we did not have any equipment at that time to study buckling. So the only equipment that we had is a brand new 250 kilonewton actuator. Right? So what do we do with that? The only thing we could do is bending. So we started looking at how to use this actuator to study and do something so that the fellow will get a PhD. So that was the objective with which we started this thing, and it came out very well. So this is the direct strength stiffness method for sheathing based design of cold form steel members. And this is a webinar that I gave to CFSI, Cold Form Steel Structural Engineering Science Institute or something like that in the US. So they called me for that webinar. Even now you can go and hear it, but I think they'll charge you for that. But this is free of charge, right? I don't know what is happening here. Okay. Okay. Now let's talk about bracings. Bracings is an interesting thing. There is one of the greatest person who worked in bracing is Joseph Ura from University of Texas at Austin. I think he worked on bracings for almost 45 years, if I'm not mistaken. Right? Anything and everything you want to know about bracing, he's already done it. J. Ura, one of the accomplished structural stability researchers of our time. I think he's still alive. Right? Now bracings there are several different types of bracing. This is a bracing that you see in bridges. My PhD was in bridges, curved bridges, so you can see this X frames, this is called cross frames, right? And you can also have lateral bracing here at the top, here for hot rolled steel portal frames. You can have blockings. This is called a blocking, and I think Professor Kao uses the word nogging. Blocking is equally the same meaning. Blocking or bridging or nogging all are the same here. That's also a type of bracing, right? So this is this, and you can also have BRB, buckling resistant braces here, right? For the cold form steel, you can have this turnbuckle here, and we can also have this bracing for energy dissipation. So there are several different types of bracings that are available, right? And one important thing is that we have been ignoring bracing in the design. What is that? We can also use a sheathing board as a bracing. So this is the wall panel, right? So this wall panel, actually you see that there is a bottom track, there is a top track, and then you have the studs here, 3 studs, and then you also have this bridging or blocking, and then you have chevron type braces. This is a typical wall panel that you see. The problem is it's too clustered, right? Too much steel. Can we remove all these steels and then put the studs alone? And then can we replace this braces with the exterior sheathing, which we are going to put it anyway, right? We have to put a sheathing, exterior sheathing, and we have to put a board. It can be a gypsum board, it can be a plaster board, it can be particle cement board, fiberglass board, it can be a plywood also, and you have to put some screws on it. Is it possible to put that and let the exterior sheathing, right, can be used as a bracing, is what we wanted to study, right? So the sheathing is an inherent external cover that is attached to the wall frames. Can we take advantage of that? See, one of the interesting things about cold form steel is that it is lightweight, ease of construction and is cost effective, right? This is a picture taken by us for work done by the Ministry of Steel under the guidance of BMTPC, Building Materials Technology Promotion Council at Hyderabad in a place called Gachibowli. In Hyderabad there is a place called Gachibowli, and so they constructed what is known as alternate construction technologies, and they wanted us to monitor. So I was there involved in this project for almost 2 to 2.5 years, from the inception to the construction, and we watched that. So these are the pictures that were taken from the project, and the project was completed in 2017 or 18. It is still a living lab for us. So far nothing has been reported, and that there are 32 apartments here. People are living there. Okay, it's a G+3 for a long time. Now, the point I'm trying to make is that it is lightweight, ease of construction, cost effective, but too many bracings are there. Too many small things are there. Is it possible, can we eliminate that and act as a sheathing board can be acted? So then we need to understand what are the possible sheathing configurations that are there. Right? There are many different possible sheathing configurations. Right? This is a single-sided sheathing. Right? This is double-sided identical. The same sheathing thickness and material can be put at the top and bottom. Or it can be non-identical where the same material is there, but this T1 and T2 are there, right? They can be different also. T1 can be 10 mm, T2 can be 15 mm. That is a different thing. Or you can put one side gypsum, another side fiberglass. You can also change the material also. This is also a different sheathing configuration that is possible. So we need to first understand what are the different types of sheathing that are available and how we can utilize that. So we studied in depth about all these sheathings, right? So we said that we were going to remove this one. So this is the bracing, and then you have this clip angle, and it is connected like this. Can we remove all that stuff and put the sheathing board? And when we put the sheathing board, we will have the screws. So now we need to understand how many screws to put, what is the diameter of the screw, what is the spacing of the screw. All these things have to be taken into consideration, right? So depending upon the screw configuration, you can impose or experience, the stud can experience either local buckling or global buckling. So the lambda sub L that you see here, right? Lambda is slenderness, lambda sub L is local slenderness ratio, right? If it is greater than 1, and the global slenderness ratio E, right? Why do we call it as E? Why not we put G? Huh? Euler. So the E stands for Euler. So global buckling, so we stand for Euler buckling, so that's why we put lambda sub E. So it's a global slenderness ratio. If it is less than 1, it will experience local buckling. So whenever the slenderness is more, right, it will experience buckling. If the local slenderness is more, it will experience local buckling. If the global slenderness is more, it will experience global slenderness. What is more? Basically, we have a cutoff point of 1. If it is greater than 1, then it experiences that. So here, if you have local buckling, global buckling here, lambda sub E is greater than 1, so it is going to buckle globally, and lambda sub L is less than 1. So these are the criteria in which you define it. Say this is basically telling that it is buckling in this direction. You see this curve, so it is buckling outwards. You see this, it's a detailed diagram. It is coming this way, it's bowing that way, right? So these are the things. We studied this in depth, right? And these are the publications that we got. A series of publications that we got in Journal of Structural Engineering proving our efforts. It's not that easy to get all these things published here. So you really need to have a lot of technical content in order to get this stuff done. So what we did was that we replaced the screw with the equivalent stiffness, and we call it as Kx, Ky, and Kφ, where Kx represents the stiffness in X direction, Ky represents the stiffness in Y direction, and Kφ represents the rotational stiffness, right? So we can replace the screw, because that's what the screw is basically doing to do, right? So if I have to come up with an analytical model, I need to remove the screw. So this is what I took into consideration. So having said that, we'll talk about Kx, Ky, Kφ, but we wanted to understand that, so our objective is, this is global buckling, right, which is not sheathed, but when I put a sheathing at the top and put a sheathing at the bottom and I put a screw, okay, this is self-tapping screw, right? I told that this edge is more like a drill bit. So the drill bit is attached to the screw, and you see that there is also a washer here. So there are several different types of screws. The one with the washer actually is very good because it will absorb more indentations and then it will have more plasticity. Okay, it will deform for a large amount depending upon the type of screw. And when you put this, it's not going to buckle globally, it is going to yield. Right, so that's the beauty of sheathing. Right, how much do I get improvement in sheathing? That's a question. Right, it's a function of your cross section. So there are three different types of cross sections that we studied. One is a C channel, another is an hat section, the third one is a Z section. The C channel is a singly symmetric cross section. The Z section is a point symmetric cross section. And the hat section, once you put the sheathing, it is not an open cross section, it becomes a closed cross section behaving more like doubly symmetric. Right? It becomes a closed cross section. And what we saw was something interesting. The C section, if you put the sheathing, it can go up to 80% as the improvement in capacity. Z section, it can go to 400%, and hat section, it can go up to 60% improvement in capacity. So it's not just, you cannot say that I put the sheathing and I get double the capacity. No. It depends upon a variety of factors. It depends upon the sheathing thickness, the type of material, the number of screws, the type of screws, and the slenderness of the cross section, as well as the shape of the cross section. All these factors determine how much capacity do I get. Right? So this is a summation of what our test results indicate. Now, I'm not the first one to study sheathing, to be honest with you. People have studied sheathing for a long period of time from 1940s, you know. Right? They have studied many things. And we have also several design standards for sheathing. This is the AISIS 100. Okay. And the section C 2.2 and 2.3 talks about sheathings, 16.1 talks about it, 2.2.4 of Appendix 2, and 2.2.7 of commentary also talks about it. And then there is a full report on sheathing braced of wall studs, ASI RP13 research report 13.1 talks about the sheathing. We also have a ASI 210 talks about the flooring and the roofing system. Section B4 talks about it. And we have another standard, AISI S400, which for seismic design also talks about sheathing in section E5 and E6. But despite this availability, they are not directly applicable to the design of wall panels. Right? They are very generic, and there is a need to verify for each loading case, which is that we need to know what type of loading and what type of sheathing is required. We'll come back to it in a minute. So let's look at C2.2. What is C2.2 of the AISI? Says that the bracing of a beam for a check. It says that where both flanges, right, the top flange and the bottom flange are connected to the deck, right, or sheathing materials in such a manner as to effectively restrain lateral deflection. So there is no movement of the connected flange. No further bracing is required. So they say that no further bracing is required if you simply connect the top flange and the bottom flange with the sheathing material effective enough to restrain in the lateral direction. Now, what it does not tell, the design engineer is someone who actually needs to be told exactly what needs to be done, because we are nation builders, we create. We need to be very specific, detail oriented, right? Devil is in the details. So it doesn't tell you what CFS cross section, what is the sheathing material, what is the minimum thickness of the sheathing requirement, what is the spacing between the sheathing fasteners. I'll also tell you what type of fasteners should you use. Right? None of which is available. So it creates a confusion. It's a generic statement, but we cannot apply it. Right? Interestingly, I think about it, in Tamil there is a saying, Etu Suraka Kari Kudavad. Because what you draw as a pumpkin in a blackboard is not going to help you cook your vegetable. Right? So it's not going to help you. So you need to know more details about it, right? So that's where it is. So it is very generic. And let's understand the mechanics of it. What actually should we do here? This sheathing fastener connection should be stiffer and stronger enough to dissipate the force or inhibit the displacement of the CFS structural member, which means that we need to be very clear about the screw, the diameter of the screw, as type of screw and the type of washer that is there. So we did a good amount of research on that, and we also got a publication here in JCSR. So let's look at in depth the mechanics of sheathing. right? If you don't put a sheathing here, right, this is called unbraced, right? Unbraced means there is no sheathing. So you have several different types of failure modes here. So this is the member which is ideal, it does not buckle. Then you have minor axis buckling, you see the picture here, minor axis buckling. This FT is called flexural torsional buckling. The third one is called local buckling. The fourth one is called distortional buckling, right? Minor axis, flexural torsional, local buckling and distortional buckling. Now, this is all individual failure modes, but in reality it is always complicated. Nothing is, black and white, it's always gray, right? So they interact. What do? Global distortional interaction buckling, local distortion interaction buckling, or global distortional local interaction buckling. So you have several different interactions that takes place without the sheathing. So why do I say without the sheathing? Because it is unbraced, right? So, but in reality, this is the picture taken from the project site I told. We have sheathing. This is a particle cement board, right? So we put this particle cement board, we put a screw. Now, how does it behave once I put the sheathing? That's what I'm trying to understand. So when I put the sheathing here, this is a sheathed column, right? When I put a sheathing here, I put so many screws here. The D sub F is the distance between the screws, right? So when I have this one, what I'm doing is that I am not going to go through a whole minor axis buckling. You see that without sheathing it is buckling like this, minor axis. But when I put the screws, I'm actually getting a minor axis buckling, but the length is between this and this, this and this, this and this. So although it is minor axis buckling, my unbraced length is significantly reduced, which means that when the unbraced length is significantly reduced, I can actually increase my load carrying capacity, right? So that's the fundamental change in behavior because of putting the screws. Now, or I can experience major axis buckling, which was not possible here. See here, in all the failure modes, there was no major axis, it was only minor axis. Now, because I put the screws here, either it can go through major axis fully, which means that I will have more moment of inertia, or I will have minor axis, but now which a reduced distance between the screws is the unbraced length. So the unbraced length is significantly reduced by putting a sheathing, in which case I have drastically changed my failure mode. My intention is to change the failure mode so that I can carry more load, which I have accomplished by putting a sheathing, right? Now, this is for axial compression. Now, what happens when it is subjected to bending, right? In column, there are three major types of failures, global buckling in columns. What are the three major failure bucklings column? Flexural buckling, torsional, flexural torsional, okay, and torsional. Flexural, torsional are the three major column buckling failure modes. But when it comes to beams, it is lateral torsional buckling, right? So I have this member, it is subjected to lateral torsional, but now you have this sheathing, it is going to more and more going to fail due to flexure. So that is the understanding. Now, if the bracing demand is greater than the stiffness that I provide, I cannot, okay, avoid twisting. It will twist like this because the demand is greater than what is supplied, right? So here the bracing demand is greater than the supplied, so I am going to have that kind of a twisting because that's the nature of the beast. The beast wants to rotate when I am subjecting it to flexure, right? So in order to arrest that, I have to provide a bigger sheathing or a proper stiffness. If I don't provide that, this is the failure mode I have. Now, if I provide a better sheathing which is greater than the bracing demand, I will not experience that, I will only experience only flexure. This is the mode of failure that I want, but it is a function of the sheathing that I provide or the sheathing stiffness I provide, right? Not only that, it also is a function of the screws. So you cannot isolate the sheathing behavior without the screws. The screws, the sheathing board, the thickness of the sheathing board, the spacing between the screws all act as one single entity right? It's like a milk. Can you tell me where is the cheese, where is the buttermilk, where is the real milk, where is the 2% fat milk? No, it's one package, right? Likewise, when you design for sheathing, you cannot isolate and study it. It has to be a one single entity acting together, and mean to understand it in that own fashion, right? Now, we did a lot of experiments. We played in the lab, right? We got a brand new 250 kilonewton actuator, right? So this is from MTS. We opened the box. I still remember the box, shipped from the US, from Minneapolis, Minnesota. And then we opened it and we carried out close to 178 full scale tests. Okay, because it will tell you the truth. It may be an ugly truth, so be it, but it will tell you the truth. Now the truth is more important, because when we write the design specifications, you need to understand the beast in its entirety. So you have to vary so many parameters in order to study that, to have some meaningful conclusions. Not only we studied full scale testing, but we also studied the sheathing fastener connections, and we carried out 111 tests. And this is a unique test setup that we developed to understand the different type of sheathing connections, and we carried out 111 tests, right? So I'll come back to that, but just keep in mind, this test data were very valuable and helpful to come up with our design codes. Now, understanding the design codes, okay, the failure modes, and verifying the applicability of the current design provisions or ASI for out-of-plane loading. So what we did was that first we wanted to understand, we got a lot of test data. Can we use the existing ASI design provisions to arrive at some meaningful conclusions? So the basic need was to understand the failure modes and verify whether the applicability of current design provisions that is there in ASI for out-of-plane loading. What is out-of-plane loading? Flexure, right? So for bending and flexure are the same, it means the same, right? So for out-of-plane loading, okay, can we use the ASI design provision? That's the fundamental question that needs to be answered. We have the data, they have the equations, whether the equations will fit the data that we have got, right? So let us look at it. So we did, as I told, 176 full-scale tests with 8 feet, and we studied singly symmetric cross-sections, we studied doubly symmetric cross-sections, which is hat section, singly symmetric is C sections, and we also studied poised symmetric cross-section, which is Z sections. And each one of them, it was 84, 6, 60, and 32. And we also studied with different sheathing materials. So we studied with the gypsum sheathing, which is a soft sheathing. We also studied with particle cement board, okay, 50 specimens, and we also studied with plywood sheathing, 27 configurations, right? So we varied the cross-section shape. We also varied the type of sheathing that we used in order to have a meaningful understanding of what this fellow is doing, right? And this is the test setup that we used for carrying out this one. When we started it, we quickly realized that the existing simply supported boundary conditions is not going to behave properly as boundary conditions, because we have a bottom sheathing, we have a C channel, and we have a top sheathing, because that's a wall panel we are subjecting bending. So when we rest it on a round circular thing, it won't give you the simply supported, because simply supported means that it has to prevent twisting at the ends. When you apply the load, it is bound to twist, right? But also at the same time, we cannot keep it so tight that it will not warp. So we have to keep it free to do anything, but we have to keep it against twisting. So we have to come up with a new test setup. That's what is shown here. So this is a new test setup. You have a series of plates assembled, right? And then you can insert the wall panel here, and then we can lock in this X direction and also in the Y direction. Okay, and this test setup was so good that we can change the different configurations, right? We can increase the depth of the section, or you can increase the width of the sheathing, but still it will accommodate. So we wanted to have something that can be reused. We cannot have 176 boundary conditions, test setups for 176 tests. So we wanted to have something it can be reused, right? So we came up with this test setup, and it's an easy test setup. Now we locked in this one. So this B shows you the width in the adjustable in the width direction. In the depth direction, we can adjust by altering the screws here. Here we can adjust the width of the panel here. So this is a very simple test setup. We can actually tighten the screws here, and then we can do a good job here. And C is the complete test setup. We loaded it here, and with the hydraulic actuator, 250 kilonewton MTS actuator, with a displacement rate of 0.01 millimeters per second. Right? So we wanted to load it slowly, because it's a baby, as I told you. It's a load it slowly and understand what it is telling us. Right? Now, it rotates like this. This is the D, is the detailed, it's a isometric view. And when you look at it from this direction, you can see that it is the round test setup, but that the entire test setup is sitting on it. But internally, this fellow is locked in so that it will not twist. The objective is to prevent it twisting at the ends. Right? So we kept it. And to look at it, we also did some track or hold on connection at these locations to make sure that this fellow does not come out, because this is the stud and this is the sheathing, and then we had a track in order to make sure that it does not come out. So these are the details that we carried out. And this is the actual test setup photo that you can look at it here. Right? And so the distance between the two is 800 mm. Right? Loading. And the distance between the support and the point of load is 725 mm on both sides. Right? And we also we were doing so many tests, we would be confused which test belongs to which. So we put a board here, and we said the specimen number, channel cross section, specimen number, thickness, everything is there. And then we take a picture. The next specimen will erase it, old school tricks, but still work. Right? So that it is very easy for it to do this one, because we took thousands of pictures, and it will be very difficult to figure out what picture corresponds to what specimen. You'll be confused. Right? So we wanted to have a very clear-cut system. That's what we did. And we wanted to remove all these fancy, LVDTs. Today, if I have to do that, I do digital image correlation, but we did not have DIC at that time. So we used NCDT, which was available here. And we generated test results, and we has got published. This is called the direct strength stiffness method for design of sheathed cold form wall panels. Recommendations for the AISI 100. So we have given the recommendations for AISI 100 and how to design the direct strength stiffness method. So let's look at the test results. The test results are very interesting. We wanted to study the effect of sheathing thickness and the fastener spacing. It's not rocket science. We know exactly what it is going to tell. We know that thicker sheathing, closer spacing is going to give you higher load. It's very simple. But the quantification, and in fact it is indeed correct, requires some kind of a test data. So we used two types of thickness. One is 12.5 mm thick sheathing board, another is 15 mm thick sheathing board, both of which were from Saint-Gobain. And then we used two different spacings. One is 150 mm and another is 300 mm. The 300 mm spacing, we got it from a specification in the US. They say that for plaster boards you cannot exceed 300 mm. So that fixed the upper limit, right? The Georgia Association for something like that, housing association, we got that. And then we had another one, is 150 mm. So we wanted to study the two extremes, 150 mm and 300 mm. So when we had this, as expected, the thicker sheathing and the closer spacing gives the highest bracing effect. So what is the thicker sheathing and the closer bracing here in this picture? Which color indicates that? What's that?
Green color.
The green color. So the green color is the thicker sheathing, 15 mm, and the closer spacing is 150. So that's the one. So you can look at the green color on top of everything. Right? But at the same time, you also look at it as and when you go from 15 mm to 300 mm, say, the green color becomes the dark green here. And then from 15 to 12.5, it becomes red, and this becomes 150. The weakest one is the thinnest cross section, and the highest spacing distance, 300 mm. So when we go for 12.5 and 300 mm, we get almost every one of them has the lowest one. So this is the blue here, blue here, blue here. But one thing that you can notice, loading criteria. We also wanted to study how it is going to affect the slenderness. So we classified into two different types of slenderness. One is a low slenderness, another is a higher slenderness. So the lower slenderness is lambda sub e, the higher slenderness here, the slenderness is between 1.25, 1.28 and 1.13. All of them are global slenderness, lambda sub e, right? So we can say that when the slenderness is low, the amount of increase in capacity is only very low, 43, 68 and 53, not much. Compared to high slenderness where it can go up to 173%, 470 or close to 600. So the sheathing is working very well when you have high slenderness, right? High slenderness is basically, it's a very thin cross section or very deep. When you calculate the slenderness ratio, it gives you, right, very, very high slenderness. And when you have a very high slenderness and you put a sheathing, the sheathing is working very well. What is the reason for that? Is it? In general, just don't worry about local.
It is very favorable under global. But in low sections, global major axis not occurs easily.
See, when it is highly slender, right? Say for example, you have a wet cloth and a dry cloth. Partially wet cloth and a dry cloth, right? So if there is a water, I use a dry cloth, the moment I put the dry cloth and wipe it like that, the entire water will come, it absorbs. If you have a wet cloth and I put on top of something, it won't absorb as much as it is, right? So this highly slender cross sections is like, you know, you have been starved for food for 10 days and then you get a curd rice and a pickle, it will taste like amrit, right? So this is very slender. The moment you put little bit of sheathing, the amount of load carrying capacity tremendously increases. But if you have already saturated with paradise biryani, like in Hyderabad, and if I give you, you know, whatever I wanted to give you, you may not have the appetite to eat more, right? So it's already here, low slenderness, and the sheathing is only going to improve a little bit. Whereas this is high slenderness, the moment you put the sheathing, it is tremendously increasing. You understood what I'm saying? And this dotted line represents the results that you get from unsheathed design strength. This is the unsheathed, remember, and this is the 43%. But this is the unsheathed here, and you can see this one, and the increase, right? So much increase because of this one. Now, we also wanted to understand the failure modes, right? So there are several different types of failure modes. As I told you, this fellow is singly symmetric, this fellow is point symmetric, and this fellow is almost doubly symmetric once you put the gypsum. It becomes a closed cross section. So for singly symmetric and point symmetric, it is always through pull-through failure. My friend here was telling about pullover, right? So this pullover and pull-through are almost synonymous, right? So the screw stays in place and something like that, the sheathing comes out, right? So that is what is happening here. So these are the failure mode that we observed in sheathing for singly symmetric as well as point symmetric. But when you have a hat cross section, I think this LTB is significantly restrained by the gypsum sheathing and you have only local buckling. Why is that? You understand my question? When there is singly symmetric and point symmetric, you have pull-through failure. The screws are not effective, right? But the same thing, the specimen is the same, right? But you change, right? This 150 and 12.5 is the same. But when you change the cross section, the failure is not pull-through, it is restrained. LTB is lateral torsional buckling is restrained by gypsum sheathing and only local buckling happens. Why is that? Huh?
It becomes kind of closed.
It becomes a closed cross section. What is the beauty of closed cross section? What is that? More resistance to? How do you know that it gives more resistance to torsion? Right, but what is the equation for calculating that? What is that?
1 by A to R naught.
How do you calculate torsional resistance?
Sigma
Huh? GJ. So what is G and what is J?
Shear modulus center and torsion.
Saint Bernard's?
Torsion cross.
No, it is called polar moment of inertia, right? No, it is not correct. Polar moment of inertia only for circular cross sections, not closed, circular. Only for circular cross sections. If you go and talk to your undergraduate teacher, okay, he would have taught you mechanics of solids using I sections for bending, but when it came to torsion, he used circular cross sections. You should ask why this discrimination. Why are you not teaching me torsion in I sections, but you are using circular cross sections for torsion? What is the answer? Circular cross sections do not warp, and the simple torsion theory G by J equal to, right? It's all working very well. So sigma by Y equal to M by I equal to E by R, same thing, right? You can replace it with simple torsion equation, it will work very fine. In such situations, your J is your polar moment of inertia, which is Ix plus Iy. But the J is not a polar moment of inertia, it is called a torsional constant when it is non-circular, right? So the non-circular J is a function of two things. One is whether it is an open cross section or is it a closed cross section. When it is an open cross section, the value of J is given as the value of J is given as J open okay, J closed okay, this is the J value, right? So there is a fundamental difference. So you can manipulate your geometry. I'm again telling you, you can manipulate your geometry and achieve your desired objective by doing this, right? So what is T here? T is the thickness, right? So if you have a cross section like this, right? This is B1, this is B2, and say this is B3, and this is thickness is T, right? Or this becomes T1 and T2 and this becomes T3. What is this? 1/3. Okay, B1 T1 cube plus B2 T2 cube plus B3 T3 cube. Right? This is how we calculate J. Right? Whereas if it's a closed cross section, right, this is D1, okay, T1, so D2, okay, T2, D3, T3, and say D4, T4, right, say for example. Now what do you do here? The A is not the area of the cross section, it is the enclosed area, right, this is A. So you plug it in here, it becomes 4A square, right? 4A square is what? So basically you find out the area of that enclosed area, right? And divided by ds by t is d1 by t1 plus d2 by t2 plus d3 by t3 plus d4 by t4, right? I'll tell you one interesting thing. If you calculate this J closed versus J open, J closed could sometimes be 1,000 times better than J open. 1,000 times. Just by manipulating geometry. Right? So your open cross sections have very less torsional resistance compared to a closed cross section. Right? So this torsional resistance is very important because torsional resistance will offer resistance against twisting. Lateral torsional buckling is all about resistance against twisting, and this fellow that you see here is a closed cross section once you put it here, right? So you'll have resistance torsion. So LTB, lateral torsional buckling, is restrained by gypsum sheathing, and hence the next failure mode is local buckling. It goes to local buckling, right? So that's the beauty of this one. Now we also wanted to study, right? We wanted to study the effect of gypsum sheathing for doubly symmetric and singly symmetric cross sections. So what are singly symmetric cross sections? Here, which is a C section, and doubly symmetric cross section is the H section, which is a hat section. So when we see that, the doubly symmetric cross sections always failed at local buckling, and the load carrying capacity is much higher, right? This is the unsheathed one without, but once you put the sheathing, it transforms from an open to a closed one. This is My, right, yield moment. It is exceeding the yield moment almost and always, irrespective of your thickness as well as your spacing between the screws for the ones that we tested, right? Now, for the open cross sections, we failed that it is always pull-through failure, right? Simply because it is an open cross section, there is no resistance against torsion, it simply twists, and hence it never reaches the yield, always failed below the yield. So cross sections do matter, shape of the cross sections do matter. So that's what we came across. So the same gypsum sheathing can behave differently for doubly symmetric cross sections compared to singly symmetric cross sections. Now, before we develop this direct strength stiffness method based on the experimental test results, we wanted to check the appropriateness of the current AISI design method, right? So let's take a check at this one. So what do we do here? So this is the AISI report on sheathing braced designs of wall studs, right? Research report 13, right? It is published, it is available in open forum, you can download it, read it, right? So we wanted to check the appropriateness of the AISI design method, and what we realized, it is not only about the failure mode, but it also depends upon how you incorporate the stiffness, right? The bracing effect of sheathing in the design. So let's look at how AISI is doing that sheathing design. The AISI is telling you that you have to adopt step 1, step 2 and step 3, right? Step 1 is determine the sheathing stiffness. What is the sheathing stiffness? Sheathing stiffness is to calculate the stiffness offered by the screw, right? So the screw basically is offering stiffness in 3 directions. Kx is the lateral stiffness, Ky is the vertical stiffness, and Kφ is the rotational stiffness, right? There are equations for that, and then once you have calculated that, you use CUFSM. So I was told that it is not Cornell University finite step method, it is called constrained and unconstrained finite step method, right? So now let me use that for technical correctness. So you plug this in CUFSM software, and then you can get a different set of values that takes into account the sheathing stiffness that you calculated by putting Kx, Ky and Kφ, right? That is applying simultaneously all the 3 stiffness. When we do so, this is the signature curve that Professor Kav has been talking, right? Local distortional global buckling, right? This is local distortional global buckling, right? And when you put the step 3 here, this unsheathed slenderness here is significantly increased when you put the sheathing, right? Just by putting the sheathing effect, the slenderness is altered, right? And the sheathing stiffness is a function of the screws, is a function of your thickness of the board, it is also a function of your material property of the board, right? It could be gypsum board, it could be plywood, it could be particle cement board, but it does alter the behavior. And what are we doing here? We are applying Kx, Ky, Kφ, and then putting it in CUFSM software, get a different type of a slenderness. Once you get this slenderness, you put it in DSM and you get the values. So Kx is lateral translational stiffness, the resistance offered by the sheathing against the shear force developed at each sheathing fastener connection when the CFS stud in the sheathed panel moves in the lateral direction alone due to weak axis buckling. Weak axis buckling is called minor axis buckling. Ky is the vertical stiffness, the additional stiffness that the sheathing adds to the major axis bending rigidity of the stud, right? Kφ is the rotational stiffness, the resistance offered against the cross-sectional twist or rotation of the flange attached to the sheathing. So we have studied this one, we have assessed it, and we have come up with a publication also. You can look at this publication and you can read more about it. Now, ASI 2013 report says that this is the equation for calculating the lateral translational stiffness. So you have this equation, ES is the stiffness board, T is the thickness of the cold formed steel, and TB is the thickness of the board, and all these equations can be plugged in and you can come up with this one, this Kx. You can calculate it. Put program in Excel, you can calculate it, not a big deal. The next one is your vertical stiffness. So it includes the flexural rigidity of the sheathing board. Again, you have this equation, right? This equation gives you the vertical stiffness Ky. The third and the most important thing is the rotational stiffness Kφ. You can see that it is empirical in nature. It has Kφ equal to 0.00035 ES T square plus 75. And that is based on some experimental test setup that AISI says that this is how you have to use this test setup to arrive at Kφ. Now we have lots of concerns regarding this test setup, but we'll come back to that later. But this is how you do it as of today. Right? Now, let's compare the design results and experimental test results. What happens when we compare our test results with the design equations given in AISI? Right? So this, we have again published a paper in JCSR, Journal of Construction Steel Research. More details are there. So what we found out is that when we put it in, the slenderness, 1.33 unsheathed slenderness, is significantly reduced to 0.3, 0.29 when we add Kx, Ky and Kφ. From 1.33 it is decreasing to 0.3, which means that it has become very, very, very less slender. Less slender means more capacity. Right? Now we see that because of this one, there is a tremendous increase in capacity. This is the unsheathed one, and these are all the sheathed ones here. Now, when we do so and we compare with the experimental test results, it is very shocking. It is shocking because 12 specimens are failing out of the 20 tests that we carried out. 12 specimens are failing, right? So you see this is the unsheathed, right, slenderness, global slenderness, lambda sub E. You put the sheathing here, it is drastically reducing to 0.3, and because of this reduction, we get a design moment is DSM. Using this DSM, we got 2037, but our experimental result is 1.1516 kilonewton meter. DSM shows 2037. So when I do M experiment by M design, it should be greater than 1, but it is less than 1, it is 0.74. And out of 20, 12 is failing. So which means that something is wrong. Right? Something is, what is wrong? So that is what we wanted to find out. So when we looked at it, right, when we put all that stuff, right, the ASI design equation says that nothing wrong is happening, everything is good, but the test results say that it is failure, LTB and pull through. The test results indicate that the failure is due to LTB and pull through, but you can see that this actual failure is like this, signature curve, but ASI predicts yield failure, it is going up like this. Right, so it's a signature curve you get when you put the sheathing. Right? So there are two ways of doing this Kx, Ky and Kφ, because one is for using table method, one is using the equation. So Kx, Ky is same, Kφ, the ASI design report gives one using equation, one using tables. We did both, right? And we have plotted it here. And we can see that ASI predicts yield failure, but in reality it is an actual failure is happening, and this is how we see that. And we have published this again here. So we suggested certain improvements in ASI design methods, right? And it got published and our results have been accepted. Now, DSM is not wrong, it is a philosophy, right? Nothing wrong with it. But now the philosophy will be correct only when you apply the right input, right? So we wanted to check the input, whether there is something wrong with the way we calculated the input. So we looked at this is the equation for kx, this is the equation for ky, and this is the equation for k phi, right? This is as per ASI. Now, what we felt was that there is something wrong in the way that ASI is understanding the fluxural loading case, right? So if you look at it, these are the test setup that were used by ASI to come up with kx, ky, and k phi. So they are putting this one, and this is the C channel. You can see that it is screwed here. There is a C channel screwed here, and they are pulling it up. This is the test setup. So what is happening is that these screws are subjected to bearing, right? But that may work very well for axial compression, because in the failure of the axial compression is the screws are failing in bearing, right? But they may not work very well when it is subjected to twisting, because flexural loading introduces what is known as lateral torsional buckling, right? Lateral torsional buckling, by definition, the member is going to twist, right? So the fellow is not going to be in bearing, the fellow is going to be in twisting or tilting. So the test setup that you have used to calibrate or to determine your kx, ky, k phi is based on an incorrect test setup, right, which gives you the stiffness values, which works perfectly fine for axial compression, perhaps not for flexure. But unfortunately, the AISI does not differentiate between axial compression and flexure. It says stiffness is stiffness, you put the kx, ky, k phi, it works fine. But what the screw undergoes in axial compression is not necessarily what the screw undergoes when it is in flexure. So that is why we say that this is the failure mode for axial compression and this is the failure mode for twisting, for flexure. So you see that this is how the sheathing breaks. It is tilting here, nothing happens. This is how it happens. So you need to understand that this screw will not carry much load. This screw will carry much load because this is bearing, this is not bearing, this is called pull through. Right? Now, so we did something. Why rock the boat? Is there some jugaad that we can do in order to use the same equations that are there in ASI but still make it work? So the first combination that we did was we put kx, ky, kphi all together as told by ASI. Now we thought that something is wrong because it is artificially stiffening, which is not present in reality because our test result shows that the reality is different. So we thought, let us remove one stiffness, and we said combination 2, we said that we'll remove kphi and put kx and ky, and we study this. When we did so, again the failure mode is remaining the same, kx and ky and k phi removed. The deformed shape is like this, but in reality the deformed shape is twisting, right? So here you see that we did it for both unlipped, unlipped. We can see that the actual failure is here, right? But ASI tells this is the failure, even when k phi is removed, right? For both lipped and unlipped, we can see that it is not simulating the actual failure mode. So what did we do? We went to combination 3. We said that let us remove kx and we use ky and k phi. And interestingly, what we found out was that actually the test results and the ASI prediction, if I remove kx, actually is working very well. And it is not only the deformed shape is also not straight, it is also twisting. So it is actually the failure mode is very similar to what we experienced in the experiment. So when the failure mode is matching, the results are more than correct, right? So that is what we did here. So what we did not do anything, we did not rock the boat. Let's use the same kx, ky, k phi. Okay, boss, when it comes to axial compression, you follow kx, ky, k phi, but when it comes to flexure, please remove kx, because kx is artificially stiffening in the lateral direction, which in reality is not available, right? And from the test results, so use ky and k phi, and the combination 3 actually works fine. So when we did that, so this is combination 1, kx, ky, k phi, for a different set of results. 6 is failing, kx and ky, 6 numbers of specimens are failing, but when I put ky and k phi and remove kx, my M experimental by M DSSM 3 right? By removing kx and using only ky and kphi, none of them are failing. Everything is greater than 1.0. So now I don't have to do anything. I use the same ASI equations for flexure, but I will not use kx in my input, and I get the output without the kx from the CUFSM software and run the numbers. It works perfectly fine. So this is our test results, right? But if you look at it, truth is always not 100% true. People say that world is made of 70% water and 30% land. But what is below water is again land only. So there is truth, there is absolute truth, right? So the absolute truth is it will work only for C sections, not for Z sections. So when you change the cross section, the jugad that we did by combination 1, 2 and 3, it doesn't work, right? So it is not working for Z sections. And again we publish this. We don't hesitate to tell what we found out. Even if it is bad, we tell it. But people like it and we get it published. So we have documented it by saying that this method will not work for Z sections. It will work for C sections, right? But as an engineer, I cannot be discriminatory in nature. I have to treat all the cross sections the same, right? So if you want, as a design engineer, you want to use a C section, you want to use a C section or a Z section, but our design equations has to be capable of doing everything. So what we looked at it, there is something wrong with the formulation of kphi. That is what we found out, right? Kx may be okay, kphi may be okay, ky may be okay. Kphi, something is wrong. What is wrong is that this equation kphi that is provided by AISI is a function of two things. One is E sub f, which is the Young's modulus of the CFS stud, and T. T is the thickness of the CFS stud, right? Nothing else. This equation is a function of two parameters. One is E sub s, which is the Young's modulus of the stud, and T is the thickness of the stud. We have serious concerns about that. I'll tell you why. As per ASI, the stiffness provided by this cross section and the stiffness provided by this cross section is the same. The depth is never a factor. The shape is never a factor. It all says that you increase the thickness, right? So one is say 50 mm, another could be 200 mm. The stiffness as per ASI equation is the same. How can it be? It cannot be the same. The rotational stiffness offered by the two cannot be same. So we said that this is something that we cannot accept it. We need to look at something very different. So what did we do? We say that the conclusion is the AIC's predictions are not matching with the experimental results for flexural loading. This is our primary conclusion. We also say that the reason is the stiffness is not matching, and the AIC stiffness predictions are not applicable due to non-consideration of influencing parameters. Several parameters are there. None of these parameters are considered in the design provisions. So we cannot directly use that. The solution is to simulate the real failure mode and determine the actual accurate stiffness and strength of the sheathing fastener connections through testing. So we wanted to do the testing, right? So you see this one. Actual failure of the sheath wall panel subjected to flexural loading is pull-through failure at the sheathing fastener connections. So now we have to make sure that the sheathing fastener connection should resist the pull-through failure. That is what we wanted to do. So there is no test setup actually available before we did this one, right? There is no test setup to actually simulate this pull-through failure, right? This is basically torsional buckling. So there is no test setup. So we developed a new test setup, right? How did we do that? We looked at ASI test setup, and this is how the ASI does it. And again, we have serious concerns about the way they are doing it, right? So this is the sheathing, this is the I section, they are clamping it here, and this is the sheathing board, they put a screw here, and then they put the CFS channel here, and put another screw, there is another joist here, then there is a load cell here, then there is a roller here, you move it like this, and then it is tilting, and you find out the rotational stiffness. This is how they do it, right? There are many, many difficulties associated with that, right? Depending upon the type of, member, one could fail by this kind of a failure, pull-through failure here, pull-through failure for fiber cement board and gypsum. But when it is plywood, it will not undergo pull-through failure. So this may work for certain, but may not work for other things. So you need to be careful to come up with a test specimen that has to be consistent with different types of materials. This one is not going to do so. This plywood will lead to withdrawal of fastness because plywood is not going to break so easily because it has a lot of fibers in it. Okay, gypsum board does not have fibers. Particle cement board also does not have fibers unless you introduce fibers in them. You see that here? This is inconsistent with this one. So we said that we need to come up with a exact failure mode, and this ASA cannot simulate that for various reasons. So this is a paper that we wrote on that. We say that it could fail here at this location, it could fail at the junction here. You see this at this location. There could also be tilting of this failure here at this location. It will not go because it is a small, this is the pulling force. Withdrawal of fasteners could happen, breakage of sheathing could happen, or pulling force here, or you can also break at this junction here. So many different failures could happen. So we cannot use this test setup in order to do. And more importantly, it's very complicated. The test setup is little more complicated because if I have to find out K-phi, I have to come up with this test setup, and in case, for people like India, it is very, very tough to come up with all these things. So let us try to do something that is reasonable. So what we said is that this is the proposed test setup. This is the CFS sheathed wall studs, right? Can we isolate something and it will look like this? When I pull it in this direction, pull it in this direction, this is the CFS stud, it will twist. So we have an UTM. This every engineering college in India has a UTM, right? It's very simple. So can we not have this one like this, a plate and another plate, put a CFS stud here, and then put a packaging plate, and you pull it up and pull it down, and because of the eccentricity, this will twist. It's a very simple test setup. You don't make it very complicated, right? You have the CFS here, you put a screw here, put a screw here. This is the board that you're going to test. And then you put a packaging plate here, screw it, put bolt here very tight, put bolt here very tight. Make sure that the number of the number of the packing plates, the distance is the same. You pull it up, pull it down, and then you're introducing twisting here. Very simple. UTM, it will do that, but the specimen will experience twisting. So we did that. And we actually could match the failure modes. Exactly. Right? So this is the failure mode that we saw in the small test setup, and this is the failure mode that we saw in the actual failure, large-scale test specimens. And we did not stop. We carried out 111 experiments. Several different types of sheathing, several thickness of sheathing, several different cross sections. We did all stuff. It came out 111 experiments. So now we have a fairly good idea how it is going to behave, because it is actually matching the test results. So now if you look at it, you see that there are two studs here. This is stud 1, CFS stud 1, this is stud 2. Right? This is a shorter stud which is 50 mm, and this is close to a longer stud depth with higher 97 mm. Interestingly, people will think that this will carry less load because it is shorter. Right? If you look at it. But the test results show that the shorter stud actually carries more load, and the deeper stud actually carries a lesser load. Why is that? Experiments always tell you the truth, but we have to understand why it is.
So
the answer is there.
The flange is very small when connecting. In CFS stud 2, flange size is very small.
That may not be. The reason we put this one is that 60 plus this plus 50 should be the same as this 40 plus. That is the reason we did it. The reason here is when it comes to twisting, when it comes to bending, you need more depth. When it comes to twisting, you need a lesser depth. The twisting capacity. Not only that, here the width is. You wanted to have the same stretch width, right? So if you add all these numbers and add all these numbers, they will be more or less the same, right? So when you have a longer depth, higher depth, there is more lever arm, more twisting, more eccentricity, and hence you have a shorter load carrying capacity. So that we could prove that using these experiments. So the lever arm variation makes these two specimens have different testing. And we did it with several things. We checked with the gypsum sheathing. We could also see that the same failure mode is replicated. When you have a deeper one, it is pull through failure. When you have a shorter one, it is actually LTB, which means that it is restrained and okay. And the CFS stud is actually restrains the LTB. And similar thing we did with several things. So hence it is validated the proposed test setup is able to predict the realistic failure modes of the sheathed CFS studs. So this is the proposed test setup. It's newly devised and we plotted lots of results in this one. I don't want to go into the gory details, but as I can say here, as the depth increases, the strength and the stiffness decreases. So we found out that the depth of the specimen is a more important parameter than anything else. So we plotted all the test results with respect to D by 2. D by 2 is the lever arm. So every one of them we plotted with D by 2 and we were able to get a very good test prediction. And what did we do? We plotted all the test results and we could find a trend here. All of them had some kind of a trend here. And what did we do? We came up with a stiffness equation. We also came up with a strength equation. We came up with a stiffness and a strength equation. It may look ugly, right? But one thing that we realized is that there is no such thing as Kx, there is no such thing as Ky, and there is no such thing as Kφ. In reality, Kx, Ky, and Kφ are all in one, right? Anybody who have studied lateral torsional buckling, your teacher will say lateral torsional buckling is 3 steps. Step 1, it will come down, 1. Step 2, it will go down like this laterally. Step 3 is twisting. Nothing can be farther from reality, right? I have carried out in my lab, in our lab with the students, hundreds and hundreds of LTB tests. Not a single specimen will go like this, and go like this. It is all combined. It comes like this, goes like this, and goes like this. Right? So there is no such thing as Kx, Ky, Kφ. Kx, Ky, Kφ is a mathematical simplicity. In order to develop lateral torsional buckling equations, they will have Kx, Ky, and Kφ. In reality, it is one stiffness that is comes like this, goes like this, and goes like this. Right? And that is also reflected in our results. So we have a single stiffness Kp, which includes Kx, Ky, and Kφ. Right? And this takes care of all that stuff. So we have equation for strength. We should also have equation for stiffness from the plots. And we applied it. Right? Our strength and stiffness actually is for what we have. What we require, we don't know. But Professor Joseph Ura had already done it. This is the requirement. He says for strength, this is you should meet this. For stiffness, you should meet that. Right? This is required. What we have come up with is supply. Whatever we can supply, we have come up with that. What is required? Already Joseph Ura had done it. So we borrowed that. What is required? What we have calculated it. And then we have said that the actual strength and the stiffness is greater than the sheathing connection. Hence, it is greater, higher than the bracing requirement. It is working fine. So this is our work. We heavily relied on Joseph Ura's work, Fundamentals of Beam Bracing, published in 2001. And we took inspiration. And this is for the columns, this is for the beams. We are focused on beams here. And what we said is that this is minimum required and this is actually available. Right? And this is for the strength requirement, for the stiffness requirement, this is it, and this is our thing. So we carried out this one, we have come up with an empirical equation, and we say that this is undesirable failure mode, right? And this is happening because you don't have fibers in it. This is a particle cement board, but when you have fibers in it, it does not come out so quickly, is actually causing a lot of failure here, so that a lot of threads are associated with that. And depending upon the type of board, we have also come up with the resistance factors phi, where the resistance factor, if it is gypsum board, we say that it has to be reduced by 50% because gypsum board is very vulnerable, it does not have any fibers, and when we have fibers for 12 mm, we said it is 0.75, when it is 8 mm, again it is not useful, but when we have plywood, we have say at 0.75 and 0.9 when we have 6 mm to 12 mm. So the same philosophy is carried out for strength as well, and we have come up with a design equation. We have published numerous results on this one. So this is the step 1. This is the direct strength stiffness method I have been talking about. So this we have already discussed. This method has now been included in IS 801 for CFS design. So the direct strength method is step 1. Is basically to design the strength of CFS structural members with fully braced conditions. Number 2, design of the sheathing board. So now we have the required stiffness for the sheathing board, beta 1, and which is stiffness and strength. And now you calculate Kp and Fp. Now if this is available greater than that, then sheathing basing design is safe. Okay. Right, so you have to calculate with required one. So basically the required one is given by Joseph Ura. You have to check with this one. Whatever we are calculating is this for the strength. Whatever we are calculating here is for the stiffness. You have to make sure that you compare with the Ura's equation, and if it is greater, then it is fine. Sheathing bracing is safe. If it is not less, go back to the drawing board, change the sheathing configuration, increase the thickness, number of screws, whatever you have to do, and go back to the drawing board and come up with a bracing requirement which is greater than what is suggested by Professor Joseph Ura. And this design predictions have been validated, and this we call it as the direct strength stiffness method that is required for wall panel design for members subjected to out of plane bending. So we verified it with the test data. This is the bracing strength required. This is the predicted. Predicted is greater than the strength. Okay, similarly, bracing stiffness required is 15, predicted is 29, so no failure. But opposite is happening here. Bracing strength required is 240, predicted is 191. Similarly, the stiffness is 25, predicted is 9.7, failure will happen. Okay, so this is basically the failure here. This is basically, you can see that this is greater than the MY, that is the unsheathed one, and it is always better. Right? Here you can see that this is the unsheathed one, but you are putting all these things, and you can see that the MDSM, it's not being matched. It is much lower than that because there is a failure here. So thank you so much for listening. Any questions, comments? I'd be happy to answer.
We incorporate that in practically we have to change the construction cycle. Because in practically when we do the construction, so we will put the CSM frame first, then the roofing done, and then come up with the boring system.
Yeah, that is based on the assumption that you don't take any advantage. That is called all steel design. You don't take advantage of the sheathing, that it is fine.
So if we want to incorporate it
Yes.
and remove that,
Yes.
so the walls will actually come up with the board particles.
Yes.
And then we will do the so
Exactly. Or you put a shoring and then take the load and then you put it and then you remove the shoring and right?
This signature this half wavelength is distance between two screens.
That's a good question. It is not the distance between two screws. He is asking, right, in half wavelength, is that the distance between the two screws? In reality, it is not between screw to screw, it is between one screw and then you leave a gap and then another screw. So the distance is not the distance between two screws, it's the distance between three screws. You understand what I'm saying? So 2 DF should come into picture. The reason is that, you know, when people are drilling the screw, we are not very sure that they drilled it properly. So we are assuming that 50% of the screws are ineffective. So let us not take advantage of screw to screw. We'll neglect one screw and take twice the distance between the screws as the unbraced length and design for it. So that's why if you look at it, And if you look at it, for some reason it's not working, but let's go through this. That's the reason you see that it is not DF, it is 2DF. You see the distance between is taken as 2DF because you are ignoring that all the screws will be effective. You are only assuming that 50% of the screws are effective. Because I have been to construction sites in Gachibowli, I have seen that how bad it is. So in India, it is very difficult to get a good this thing. In India, yesterday he was an auto wala, today he'll be a welder, tomorrow he'll be a mason, day after tomorrow he'll work in coal farm steel industry. So he will do whatever job he wants to do. So there we don't have a trained skill set. So you will not be able to get quality workmanship. So that's why you cannot be very sure about the work that is being done. So the code has an obligation and a responsibility to make sure that you need to have some kind of a redundancy, and we are saying that 100 screws are there, we say that 50 screws are ineffective. Even if it is 50 screws, this is how the results are, and still it is very good. Okay, so did I answer a question? Okay.
This spring, now 3 springs are replaced by 1 QC.
Yeah.
So earlier, when 3 were modeled, maybe, so there will be 3 boundary conditions or something. Now it will be a linear spring in all the directions.
There is no spring at all. There is no linear spring, there is no rotational spring. It is a combination of linear and rotational. Right? Linear spring is for Kx and Ky, and rotational spring for Kφ. But what we are saying is that that itself is a myth. In reality, it does not behave that way. It's an interactive mode of failure where we say that all the springs act in unison, and we see a combined stiffness parameter which it goes like this and goes like this. Right? The very definition of LTB itself, you need to understand it carefully. When you do experiments, you'll clearly notice that there is no Kx, Ky, Kx and Kφ. It's all one together. So that's the test results are also showing the same. Any more questions? Okay. You don't have any questions? We'll take a break for lunch, right? We'll come back.